What are poles in electrical engineering transfer functions? Imagine trying to balance a pencil on your finger. If you push it just right, it stays upright for a moment. In control systems, poles are like those critical points that determine how a system behaves. They are specific values of the complex frequency variable, called S, where the transfer function's output would become infinitely large. Think of the transfer function as a recipe that tells us how the input and output of a system relate. It is usually written as a ratio of two polynomials, the numerator and the denominator. The poles are the roots of the denominator polynomial, meaning the values of S that make the denominator 0. When that happens, the transfer function tends toward infinity, indicating a pole at that point. The variable S is a complex number made up of two parts, plus sigma, which is the real part, and j plus omega, which is the imaginary part. The real part, plus sigma, shows whether the system's response grows or decays over time, while the imaginary part, plus omega, relates to oscillations or frequency. Poles can be located anywhere in this complex plane, with their position telling us a lot about the system. If a pole has a positive real part, the system becomes unstable because the response grows without limit. If the pole has a negative real part, the system is stable because the response diminishes over time. The closer the poles are to the imaginary axis, the slower the system responds. Their location influences how quickly the system settles and how it reacts to different frequencies. For example, in a simple electrical circuit like an RL low-pass filter, the transfer function might have a single pole at S is equal to R/L, where R is resistance and L is inductance. Since this pole is on the negative real axis, it indicates the system is stable and the transient response decays exponentially. Engineers often plot poles on a complex plane called a pole zero plot. This visual helps them see at a glance whether a system is stable and how it will behave over time or across frequencies. Understanding where the poles are located helps in designing circuits and control systems that behave just right. Whether you want a system that responds quickly or one that remains stable under different conditions, knowing the poles is key. They tell us if the system will oscillate, how fast it will settle, and whether it will stay stable or not. In essence, poles are the points in the complex plane that shape the entire behavior of a control system or signal processing device.